Okay, so we are really talking about surrounding the idea that big O is really like a family notion about a function, like a set. Okay, let's start with the first one. We first talk about to really construct individual family. Let's say the family for big O of n versus the family of the big O of n squared. Let's talk about individual families first, and then we're going to see how we can relate different families together. Okay, let's talk about one by one. All right, you will see some definition on the slides, but I will just show you the page right away, so get intuition right away. And it is also important, oh, sorry, I forgot to switch. I beg your pardon. Okay, so you can see here, we're going to talk about this family here, and also we're going to talk about this family over here, right, individually. However, it is important for you to also try to see how the idea of this family idea can be applied to the plot that we spoke about earlier. I'll draw some connection to it as well. Right? It's also important to see. We want to connect everything together. Let's now read some text over here. We're saying each member in big O of g of n, for example, big O of n, is such that the highest power of that function f of n, for example, over here, should be less than or equal to the highest power of g of n. In this case, g of n, the power is just 1. That means any function whose highest power is less than or equal to 1 should be included in this family. When I say power less than or equal to 1, that means they grow no faster than n. Okay? I'm going to put it here. Functions growing no faster than n should be included. All right, so guys, can you give me some example? What functions will grow no faster than n? Any? 5n plus 1. Huh? 5n plus 1. Yeah, 5n plus 1, that's like a linear, right? For example, I'll just put n here. Right? So when I put n here, that includes many possibility. So when I put n here, it's just linear function. It could be it could be 3n minus 1, it could be 10n plus 2, etc. I'll just put n here. That means it's linear. All right? What else? Huh? Constant. Yes, I like it. So here I might just put, I can put n to the power 0, or I can put 1. Okay, either way. Good. There's one, another one, at least. Square root of n. Interesting. Okay, I agree. Somehow it will also grow no faster than n. Yes. Even though that one is not really including our plot, but it's a nice addition. Good. Another one? Log n. Log n. Yes, indeed. Okay, good enough. Thank you. So these are some examples that should be included in the big O of n because all these functions somehow can be upper bounded by n with some constant chosen. Or intuitively, think about all these functions here grow no faster than n. So this is where we can draw connection to the diagram. All right? Right here. So we talk about linear, which is exactly this line over here. According to our listing over here, we don't have the square root of n right now. That's okay. So here, we want to show, so this particular family of big O of n is going to include just this line itself, and also everything below. Agree? Yep, agree. That one is going to include logarithmic, log, and also constant. Okay? I'm going to write it down. So you can also understand this as like the following. So I'm going to start from here itself all the way to over here, right? That one is going to include the linear itself, the log, and also constant. Of course, square root of n will be somewhere here too. Okay. So this one I can write down the comments here. Big O of n contains all functions growing no faster than n. All right. That's one family we just finished speaking about. Let's now get to a potentially bigger family. All right. I intentionally draw that to be bigger, right? So let's now talk about n squared. All right. Let's do some similar exercise here. Give me some example, that function that should be included. Start with the largest power. Quadratic? Yeah, n squared, right? Good. So I can definitely put n squared over here. Next one, that's lower. Go ahead. No, you cannot put exponential. The reason, okay, we'll get there, but exponential, no. So first of all, let me say exponential does not belong to big O of n squared. No, it does not, okay? The reason is, which you will see, I'll do some other example, but you can try that as well. Exponential cannot be upper bounded by n squared, no way. Doesn't matter how large the constant you might choose, there's no way. Okay, just remember that, right? No. Okay, give me another one. What's the next one? N log n, I like it. Okay, n log n. Next one. And then it could be maybe a log n, agree? Also, it could be constant. And also, it could be the square root of n that your fellow student contributed. Did you notice one thing here? Somehow we are making some repetition, right? Especially if you think about this. This guy here is a family for big O of n. That family was completely contained exactly here. All right? And I'm pretty sure in 1019 you learned about how to relate two sets together, right? Subset versus proper subset, right? Kind of rings the bell. I'll get there in a moment, okay? But you want to draw some connection right away. So big O of n is, I'll say contained in quote, but we make it more formal, more precise in a moment. Within big O of n squared. And notice that n squared and n log n, they only belong to big O of n squared, but they do not belong to the big O of n. They do not. All right, that's something we'll see as well. All right, let's now go back to the graph and then make some quick annotation. So quadratic n squared is exactly here. It's a bigger family, so we're going to see a larger vertical spectrum, right? So let's do that quickly. So this one here is going to be starting from quadratic itself all the way to here, right? Right here. It's a strictly larger family. So here you can say big O of n squared contains big O of big O of n and other functions. Okay. But other function, for example, other function could be n squared here and n log n, right? That's what I meant. Are we good with this one here? All right, so the main takeaway is to see how we can construct individual family, and somehow some family may be contained in another family, and draw the connection to this plot over here. Really important. If no question, I'm gonna talk about some set theory, a little bit, not too much, lightweight. So let's still use these two families as two examples, n and n squared. Okay, I'm gonna give you guys multiple choice. Okay, let's simulate in written test. How about that? So here, relating in family. Yeah, exactly. Let me just make sure I don't miss any point. Bear with me. Yeah, good. Okay, so we talk about the two examples there. So we got big O of n, and also we got the big O of n squared. Okay, I want to relate them together. I got 4 choices for you. Either this, or this, or this, or this. Just for checking, what's this called? Subset? Okay, how about this guy here? Proper subset. Okay, you may want to review, but I'll review anyway. Okay, well, this one just saying this is a subset of that, right? For this one, just a reverse. Now, I want you guys to choose the correct relations. Correct. As long as it's correct, you should choose it. There could be one answer. There could be more than one answers. I heard 1 and 2. Do you guys agree? 1 and 2? Okay, good. Okay, you guys are great. Okay, both 1 and 2 are correct. I agree. Both are correct. However, which one is more accurate? If you say 1, think about what's happening here. If you say 1, you kind of implicitly implying that it's possible that these two sets is exactly equal to each other. Can that ever happen? Not really, because remember we said earlier, let's say if you compare these two sets over here, at least these two types of function, they only belong to this but not that. So there's no way these two sets are equal to each other. So subset, even though that's correct, but it's not accurate enough. Okay, that's an important point to make. Okay, sorry, let me just delete that empty page. All right. So we want to, so this will be correct and accurate. And let's get down to the basic a little bit. It is important for you to really know about the proper subset that we're talking about. So whenever I say S proper subset of T, right? The way to visualize it is like this. We say S over here, and also we say T over here. There are two things to say. Number one, we say that each member in S, the smaller set, is also a member in T. That one's obvious. If I say something that's in here, of course that's also in the bigger set, that's for sure. The more important point is the second one. If that's a proper subset, that means I can find at least one member in T that's not a member of S. Very important point here, okay? There is at least one member in T that's not a member in S. All right, that's just a quick review about proper subset. How do we apply this little property here into our context of big O family? Okay, let's now go back to our example about these two guys, right? So we said that the most accurate way to say that would be to say proper subset, right? That's the most accurate. Let's now do that. So I'm going to redraw that. Let's say the smaller one, strictly smaller one, should be big O of n. The strictly larger one should be the big O of n squared. Now, let's now apply that, right? Just repeat the points. This one is to say every function that can be upper bounded by n, they should be able to be upper bounded by n squared, right? Upper bounded by n can also be upper bounded by n squared, but not vice versa because it's a proper subset, right? Also, I'm going to write it down. So over here, there will be a member here. There's at least one function upper bounded by n squared, but the same function cannot be upper bounded by n. Okay. Can you give me one example? N squared, yeah, I like it. Yeah, that's easy. For example, n squared, also n log n, right? Something like that. Okay. I want to do one more illustration to illustrate this point. right? So you can now, I'm going to show you a little bit different example to show this point specifically, just to give you a little bit more elaboration. But you can also try to convince yourself why this is the case by following the same visualization, which I'm going to show to you. All right, let's now do one more. Okay. Let's now consider slightly simpler proper subset. Okay, just slightly easier for you to grasp right away. So let's now talk about big O of n to the power of 0, constant basically. So constant function family should be a proper subset of big O of the linear function. We know that pretty well. And let's consider this guy over here. Okay. Let's now visualize it first, and then I'll show you. Okay. So we can say the smaller one would be constant, big O of n to the power 0. So for example, we may have 1, we may have 5, we may have 10, etc. Okay. By the way, is log n a member here? No. Log n is definitely cannot be upper bounded by constant, right? It grows strictly faster, right? That's something that you got to study for. Just about the diagram and also the idea, right? All right, another one. So this will be n squared, big O of n squared. Okay. So let's now first start with this set over here, just to make sure we understand this. These will be all the functions that can be upper bounded by constant. Sets of functions that can be upper bounded by n to the power of 0, constant. And let's now consider in detail a member over here, right? And I'm going to choose 3n. Okay, 3n. Oh, I beg your pardon. Over here, I really meant to say not n to the power of 2. Right? Since we're considering this, right, should be n to the power of 1. It's a typo. Sorry about that. Okay, that's really what I want to write. So 3n, I claim that it can be upper bounded by n to the power of 1. Obviously, you can choose 4, for example, right? You can upper bound that easily. But I want to say 3n can never, ever be upper bounded by n0. You might be thinking, what if I choose a very, very, very large c? No, it's not going to work. No way. Okay? So you got to see some diagram. At least a function upper bounded by n1, but not upper bounded by n to the power of 0. Okay, so here, even with a very large c chosen. Once I visualize it, you will see it's kind of obvious. Doesn't matter how large the c you might choose. Okay, let's now do the diagram. Okay, so let's say this is the diagram here. Okay, so we got our f of n, and we got our n. Let's now put 3n first. That one basically like n, just slightly steeper, right? Let's say 3n here. And in order to actually upper bound it with m0, n to the power of 0, we have to choose some very large c. But as you can see, it doesn't matter how large you might choose. Somehow, constant line, like a 1, will just be a flat line. If you choose a c, as c grows larger, you will just get flat line, a little bit higher and higher and higher. The trend goes on. There must be some intersection somewhere. Doesn't matter how large the c is, right? That's a really critical insight. So I'm just going to put it here. Okay, so that will be c times n to the power of 0. So here you can assume that c is a very large value. But you can never avoid there will be an intersection somewhere over here. As soon as you got an intersection, now, do we have any upper bound effects after the intersection? No. You can see the c times n does not upper bound the actual 3n. So there's no way you can ever upper bound. There's no such a point that From that point, you can upper bound 3n just by the c times n, just no way. Okay? Think about this kind of insight. I think it's very handy. And once you thought it through, you can think about why. Like n squared and log n cannot be upper bounded by n. That'll be some exercise for you. Okay? Okay, I'll write down the last insight and then we can move on. So here you can say, despite how large C is to the right of the intersection, you will have basically C times n0 less than or equal to 3 times n, right? I'm basically saying this modified version of the Gn is actually less than or equal to this one here. So there's no upper bound effects, basically. If you check the formal definition, you will see. So this one here tells you no upper bound effects. As you can see, all the insights we are trying to discuss today, they're not difficult, but you got to be very clear about the upper bound effects and how things are put in the different order, right? You got to really study for this, right? To really make sure you can naturally recall them during the test and the exam. All right, any question about this? All right, at least on the big picture, it's clear. All right, let's now do a visual summary about this relating family thing. So what we really have is really like this, the proper subset relation. So you can have basically big O of n to the power of 0 constant, proper subset of maybe log n, proper subset of big O of n, proper subset of big O of n log n, etc. Okay? We got an increasingly growing family. So I'm now going to visualize them. I'll give you some exercises to try, which should be quite easy. Okay? So we start with the smallest family. This will be big O of 1, constant, here. The bigger one over here will be the big O of log n over here. And then the bigger one will be the big O of n, which is over here. And then we got, let's say, the next one. The big O of log n. And log n, beg your pardon. And some exercise you can try. Can you find as many witnesses as possible? What can be some member that's exactly here? What can be a member that's here? What can be a member that's over here, right? Give some idea. For example, here you want to give a function that can be upper bounded by log n, but it cannot be upper bounded by constant, right? Something like that. Yeah, it's really worth diving into. Okay. All right, the final property we're going to look at before we take a short break. Okay. Final property. All right, so the final property is also very practical. So upper bound themselves are not necessarily enough for you to actually make an accurate decision right away. Okay, I'm going to show you exactly what I mean by using some example. Okay, okay, right here. Let's now consider two functions over here. Let's say we got two functions over here. Let's say f1, that's a runtime for algorithm number 1. Let's say that one is 7n minus 2. f2, runtime for algorithm number 2. That one is 4n squared minus 3n plus 6. Okay, like that. And let's now try to draw the families and then try to locate where these two functions are. And then I'll show you some sayings. Okay. So let's start with, let's say again, we got a constant over here. The big O of n to the power 0, the constant. And then over here, the bigger one, big O n to the power of 1. Okay, and big O n to the power of 2, just one more. So big O n to the power of 3. And I should be able to move it. There we go. All right, so that'll be enough. Let's now try to locate these two functions. This one, 7n minus 2, should be here. Agree? Okay, linear. 7n minus 2. And this guy here, higher power, n squared, should be right here. 4n squared minus 3n plus 6. And let's now consider the following statements. Let me take this one, for example, 7n minus 2. Okay, this one here. And I'm going to say the following. 7n minus 2 is order of, right? Of course, that means membership, right? Remember a different way of saying big O, right? Big O of, what would you say? N, at least, right? That one I agree. Can I also say it is big O of n squared? Is it correct? Well, if you think about membership, right, I'm saying the following. This function here is a member of this set. But this function here is also a member of this bigger set. And this function here, of course, is also a member of this set over here. So all I'm saying here are all correct. I can even say big O of exponential. You can see, when you describe upper bound, if you're not being very accurate, you can easily give useless information or misleading information. That's really the point I'm trying to make. All right? So all these statements here are correct because the simple subset relationship we are checking. All right? So these are all correct. But we need to choose the one that's the most accurate. So which one should be the most accurate? Should be the one with the lowest power. That would be the tightest upper bound. How about that? Okay. So this one is the most accurate. So that would be the tightest upper bound. Right, that's important for you to distinguish between being correct versus being accurate. And let me now show you one more to see how things can get very, very misleading. I'll put it here. Okay, I'll put it here. And I will simply say the following. I would say f1 of n, the first algorithm, I can say it is big O of n cubed. That's correct. I can say f of 2 of n, the second algorithm, is big O of n squared. Let's say this. If I didn't give you any information about these, I'm only telling you this, you might tend to think which one is more efficient. You might tend to think this might be more efficient, right? If you think that way, you're making the wrong decision because now f of 2 is actually the less efficient because that's higher power. You see my point here? The point is you cannot just decide the efficiency using big O if the big O itself is not accurate enough. That's really the point to make. Okay? Does that mean f2 of n is more efficient? No. No, because the big O of n cubed is not accurate for f1 of n. is misleading. All right? That's one example to show to you. You got to be very careful. So you really want, ideally, you really want to use the source function right here. But if you really want to use the big O to really judge, it's okay, only given that they are both most accurate possible. All right? That's really the conclusion. Okay? All right? That's definitely the misleading. Okay? Misleading. All right, any question here? Yeah?
What do you mean by more efficient?
More efficient. Well, for example, you might be thinking that more efficient means the runtime will grow slower as the input size grows. So here, if you look at that, this one is linear. The runtime is going to grow much slower than n squared. So that means it's going to be more efficient asymptotically. However, if I'm only telling you this one is n cubed, this one is n squared, you might be tempting to think, oh, this one should be more efficient. That's not right, because somehow this one here is too loose. It's not really tight enough, right? Good. Yeah, again, efficient simply means it will take less time. It means the runtime function is going to grow slower, relatively. Jennifer? Tell me where? You mean here? Over here?
Yeah, and below that.
This one here? This one actually is 1. Maybe it looks like 2 to you. But that's my mistake. Okay, I'll make it more like 1. How about that? Better? Okay, good. I really meant 1. All right. All right, good. Let me say one more thing, and then we take a short break, right? Very short break. We just want to do more examples before the weekend. Okay, guys, please, one more, and we'll take a short break. The next one here, very simple. I just want to show to you, whenever you want to state the big O, when you are doing some intermediate calculation, you don't need to be 100% precise. But when you actually state the final answer, you want to make sure the big O reference function g of n itself should really drop all the irrelevant terms. So what do I mean? If you write something like big O of 7n squared plus 4n minus 2 as the final answer, no. Nobody writes like that, okay? Not appropriate as a final answer. For intermediate calculation, it is okay, right? I also do that sometimes. As the final answer. For example, if I want you to state the running time, state the asymptotic upper bound for some algorithm, you don't want to give me that, right? Instead, what you want to give to me is just the highest power, for example, with all the other irrelevant terms dropped. So that would be the one to really give, right? That's just another point to make. Okay. All right, you also see that another example on the slides, but you can take a look. Any questions? Good. So I'm going to give you 2 variants over here. Okay. So let's say I still got my contains duplicate from the previous page. I just got 2 duplicates over here. Right? Variant number 1. I'm going to modify, let's say, here, rather than here, and why don't I say 10,000? Or some large number. Doesn't matter. 1 million. Doesn't matter, just some large number. So now, after this, are we still going to get n squared? No, because easy. So if you go back here, you can see this is the highest term that's going to dominate. And n squared comes from the number of outer iteration times the number of inner iteration, right? So here we got n times n. How about now? 10,000 times n. Agree? So that one is going to dominate. Okay, so we only need to look at that one. So that one there, if you think about big O of 10,000 times n. Well, the highest power is n. Multiplicative constant can be drop. Doesn't matter how large it is. Doesn't matter. Asymptotically, any large constant is small. Okay? What we get is big O of n. Okay, not n squared. Okay, so that can maybe somehow answer your question, right? Let's play a little bit more. Can I make this loop potentially even more efficient? Make it constant. Oh, I can. Why don't I change the other bound also to be constant, right? I can say, for example, this one here, 1 million. Here, also 1 million. Sounds big. Asymptotically speaking, they are not big. So what I would get is big O of basically 1 million times 1 million. Basically, think about this as like a big O of some very large constant C times n to the power of 0, right? And I can always drop multiplicative constant, no matter how large it is. So this will still be just big O of n to the power of 0 or just 1. All right. Yeah, so hopefully these two variants kind of convince you that whenever you see the code that you're supposed to analyze for the asymptotic upper bound, don't just to see how many levels of nesting you are having. That's not the way to go. You really have to see how the loop counters are changing between the iterations and count. Okay? Any question? Yeah?
So say we have an algorithm that has two loops, a nested system with two different counters, like we have one m and one n. Mm-hmm. Would that, instead of being O of n squared, be considered O of n?
Yeah, exactly. So what your fellow student was asking is another very valid question here. I'll answer that briefly. Okay, we wouldn't see that many examples here because usually we are considering just one input size n, right? Let me put that anyway. But it's a valid question, which I like. Give me just one moment here. Let me close it. Oh, let me copy it again. So what I would do is I'm going to, copy. There we go. Wrong button, I guess. There we go. Okay, this one here. So let's say let's say it contains duplicate, right? Let me introduce another array. Let's say we got, so n here is really a.length. Okay, let me extend the parameter list over here, right? I might say there's another integer array, maybe b, like an independent array, okay? And then I may introduce maybe integer m, just for convenience. So over here, you can think about the m here is really the length of the second array, b.length. Okay, think it that way. So now I can say, of course, you can change the name. The name doesn't really make sense anymore, but that's okay, right? We'll just keep that. So let's say we change this one to be, this is still n, but we modify this one here to be m. Right? So we got different bounds over here. So what we're going to get will be ultimately just big O of n times n. Your fellow student was asking, would this be just the same as big O of n squared? No, not really, because we have no idea what's the relationship between the sizes between this array here and this array here. So for this question here, it will be sufficient just to say n times m, where here we know that n is the size of one input and m is the size of the other input. So this will be more accurate way of saying things over here. Okay. If we get into something like this later, I'll let you know. But hopefully that can answer the question. All right. Next one. All right, so this one is pretty easy, but let's now let you take a look at that for one moment and let me know what's your guess. All right. Oh, we got 3 loops over here. Should that be n to the power 3? No, obviously not, right? Good. What should be the tightest asymptotic upper bound? N squared? N squared? Okay, good guess. Okay, let's now take a look very quickly. Okay, n squared, yes. All right, very quick. Line number 2, just 1, right? Just constant operation. And then if you look at the first for loop, that one there looks linear because the loop, I counter will just go from 1 all the way until maybe n minus 1, still n. And this one here is outside the loop, but that one there also just 1. And if you look at the nested loop over here, very similar to the contains duplicate case, you got n here, so that should be n squared. And finally, you can see this one here is just n. Just 1. So what we get is big O of 1 plus n plus 1 plus n squared plus 1. Big O of n squared plus n plus 3. And you can drop the lower term, n squared. Okay. What this one tells us is the part of the algorithm that has the highest power is going to dominate the running time. Right? That's another way to see it. And of course, this one here is the most expensive part for the algorithm. Of course, it's going to dominate asymptotically. Alrighty. Final problem. All right. You guys were asking about, maybe you asked about how to change this, maybe I and J. Maybe I ask you, right? There you go. Okay, guess first. Well, I highlighted the tricky part for you already, right? You can see for the inner loop, J does not start from 0 anymore. It starts from the current value of I, which might give us some advantage, right? Because we know that gradually I is going to get larger and larger. Let's say when I is equal to n minus 1. In that case, J is going to be n minus 1, and n minus 1, just one iteration. It sounds to me, it's pretty efficient, right? More efficient than the previous one contains duplicate. It sounds to me. Or you think you're being misled?
Would it be n log n?
N log n? Typically, if you only got addition without any multiplication or division, you wouldn't get log n. Not really. Good guess. Okay, but you're claiming that it's going to be cheaper than n squared. Okay, sure. Or any one of you was somehow convinced by me it's going to be n. Nobody. I'm glad. Good. Anyone? Any other answer? Just guess. Go ahead. N squared by 2? Well, n squared by 2, n squared, right? Okay. It turns out this one here remains to be n squared, even though in the later iteration for the outer loop, I value is going to get much larger than the beginning, which will reduce the number of iterations for the inner loop, but that one there wouldn't change what's going to be derived asymptotically, right? It sounds a little bit weird right now, but we're going to show that to you. So if you only guess big of n squared, that's good. You had the right guess, but we're going to show exactly how this can be derived, right? We're going to see that. All right, so this is something we're going to follow the same approach to observe the loop pattern. But before that, let's do some quick annotation. So we're going to focus on the loop header. So we're going to focus on this loop header here in just a moment. Okay, we're going to do that. Okay. Before that, outside the loop, we got line number 2. This one here should be just 1. Right? Also, outside the loop, over here, return, that one should be also 1. And then, if you only look at line number 5 alone, that one should be just 1. That means every time you try to execute it, it's going to be 1, right? But how many times are going to execute it? It's going to depend on how many combinations there are between I and J for the nested loop. Always depends on I and J combination, okay? So here, you want to, okay. This will be it will take 1, like a constant number of operations for each execution of ij, for each execution of I and j, right? That's important to know. So now we got to figure out exactly how many combinations there are for I and j, right? That's something we got to figure out. Let's now try to observe the pattern. So pattern of I and j. And since the outer loop has I, so we're going to start with I, right? That's the first dimension. I will be from 0 all the way to n minus 1, the same as before. That one's straightforward, okay? So I'm just going to use, again, the blue for I, and also I'm going to use the purple for j, okay? Here I, and also here will be for j. Okay. All right, so I got I here can be 0, 1, 2, all the way to n minus 1. Okay? And now I know pretty well the number of iterations will be from 0 to n minus 1. That's a closed interval. And we know pretty well by the formula is n. Okay? Let's now figure out a second dimension. That's going to be trickier. Okay? If you think about it, let's say here, j. Let's say when I value is equal to 0, what would be the range of j? 0 to n minus 1, right? Okay. So here, since we're counting, so here this part we're going to be more precise. J will be starting from I value. In this case, will be 0, 0, 1, 2, all the way to n minus 1, right? You can see strictly less than n, right? Should be n minus 1. And what about when I value is equal to 1? Start with 1 all the way to? Yes, exactly. The upper bound doesn't change. It's really the lower bound that's actually changed, right? Very good. So it's going to be 1, 2, all the way to n minus 1. And for the next one, I'm not going to bother you. 2 all the way to n minus 1. And also, what about the last one? N minus 1, right? Good. And you guys can see that we got some very nice triangular shape over here. Exactly here, right? Over here. Which is good. All right, and we're not done yet. Somehow we very carefully enumerate the combinations of I and j, but now we got to count exactly how many combinations are there. So for row number 1, how many combinations do we have? We got 0 all the way to n minus 1, right? You can write down the closed interval over here. So I'm going to use a different color. So it's going to be from 0 to n minus 1. We'll know that it will be n. For the second row, is from 1 all the way to n minus 1. So it will be n minus 1 combinations. And then for the third row, it's going to be from 2 all the way to n minus 1. And then it's going to be n minus 2. Basically, the number of combinations are decreasing, simply because the value of j is increasing, right? Symmetric. And you go all the way to the bottom here. The bottom line is going to be from n minus 1 to n minus 1, just itself, one value. So what we got to calculate would be n plus n minus 1 plus n minus 2 all the way to 1. Does that kind of seem familiar to you? By the way, this kind of summation here has a name. Huh? Not factorial. Not quite. If you say n times n minus 1 times n minus 2, yes. But now we say plus. Let me write it down. Okay, I see the way the confusion might be. So if we want to calculate the number of combinations, it's going to be n plus n minus 1 plus n minus 2 plus all the way to 1. If I change this to be multiplied, of course that will be factorial, but it's plus. No. There's a name for this summation series here.
Arithmetic series?
Arithmetic sequence, thank you, or arithmetic progression, right? Either name. And I'm pretty sure you have heard about this name before. I'm going to review the sequence very quickly to tell you the formula you also need. But I want to give you some heads up. The arithmetic sequence is the easy one to really kind of remember. It's asymptotic complexity, right? I mean the asymptotic upper bound. There's another sequence called geometric sequence. That one there we also need. But when we talk about trees, not yet. But I just want to give you some heads up. I'll talk about geometrical sequence and also give you some nice proof about it very soon, after the reading week. All right, so let's now talk about arithmetic sequence, right? Very quickly. I'll just give you the facts, right? And I'm not going to worry too much about how to prove the formula. If you're interested, we can talk, maybe beyond the class, okay? So this will be the general form for the arithmetic sequence. You got I here plus I plus C plus, let me write down the whole thing and then I'll explain. And then I plus 2 times C plus all the way to I plus n minus 1 times C. All right. So let's now recall the terms. The first one here, the leftmost term, is called a star term. And I can rewrite this slightly, which will help for some later question. Think about this one here is more like I plus 0 times C. It's going to be 0 anyway, right? And then the C we're talking about over here is something called common difference. All right. And then, okay, that's good. Another term we got to also figure out is how many turns there are in this sequence over here. The number of turns. Guys, in this sequence here, how many turns are there? N, precisely, right? Do you guys know how to figure it out? See the pattern here. We start with 0C, 1C, 2C, all the way to n minus 1. So we'll get to the closed interval between 0 and n minus 1. We got n turns, right? You got to be very kind of proficient in figuring out things in the pattern. It's very important. Okay, it will be n turns. All right? So now the formula for the sum is going to be the following. Okay? You're going to sum up the beginning and the end term. So I over here plus I plus n minus 1 times C. And then multiply by the number of turns divided by 2. All right, I'm going to draw you some connection here. So this one here is a beginning term. This one over here is the end term. And also, what we just figure out over here, n is the number of turns over here divided by 2. All right, I'm just going to give you the simplification of that. You don't need to worry. You can take it for granted. This one is going to be C times n squared plus 2i minus C times n divided by 2. Right? But if you look at this, what's the highest term? Highest power, n squared. So that makes it big of n squared. Okay, that's a conclusion. So if you got a geometrical sequence, if you got an arithmetic sequence, it's going to be big of n squared. Okay, like this form. And let's now go back to where we were over here, right? So for this particular one, how do we figure out the sum, right? You're just going to say the beginning, which is n, plus the beginning turn, the n turn over here, multiplied by the number of turns, which will be n, right? We go n all the way down to 1, so that's n turns, divided by 2, right? So that one there obviously should be big O of n times n, n squared. That's the highest power, right? N squared. So this is the very important intermediate result that we figure out about given this nested loop, what will be the number of combination between I and j, okay, n squared. All right, so now we are ready to put everything together and figure out the answer totally. Big O of, so we want to do the 1 here. So this is line number 2, the sum initialization. And also plus, we got n squared times also 1. The 1 here is line number 5. And also the n squared over here is the number of ij combination. That's something we just figure out. And also plus, also got 1, which will be line number 6. Okay, let's do a little bit simplification. Big O of n squared plus 2, right? Drop the lower term, we got n squared. Right? So our initial guess was also right, but you want to show this intermediate work. Okay. All right, so that's the final answer. All right, any question about this? Good. All right, so this lecture here, the main part should be about the linked list, but we will not be able to get there today, I'm afraid, but definitely, hopefully Thursday in the later part. So this slide here, let me give you a very, you know what? Let's look at the learning outcome, so we'll see. Okay. We're gonna learn about, first of all, the basic data structure arrays versus linked list. So these two are the basic building blocks for any algorithm that you have to implement. For example, if you want to implement a queue or a stack, you have at least these two choices. Which one should you choose? Right? So that's something we're going to talk about. So there's no silver bullet. That's why we're going to talk about both of these structures. There will be certain scenario where it will be more efficient for the array to operate, and vice versa for linked list, right? So we really got to see which scenario we are talking about, right? I'll get there. And we're going to talk about two sorting algorithms. Remember the five I kind of mentioned on day one, right? When we talk about syllabus, insertion sort, selection sort, which we're going to talk about most likely Thursday. And later on, after reading week, we're going to talk about merge and quick sort, when we talk about more advanced recursion. And then the final one to talk about will be heap sort, right? So that's kind of the roadmap for the course. And for the linked list, we're going to see what it means to be singly linked and what means to be doubly linked. So this part here is really lots of fun. So you guys can bring your notebook, lots of drawing to do to really understand what's going on, right? Maybe from Thursday, maybe later part of Thursday, or definitely Tuesday next week. And we're going to see the runtime comparison between array and linked list operations. We'll see some of them for array today. And for your assignment number 2, which will be released at some point next week, and assignment number 2 is going to be about linked list. So we're going to cover some basic one in the lecture, but you guys will have to really do lots of coding yourself, which we assume you kind of grasp some coding skill from 2030 in the previous courses. There will be something required called generic list, which I'll try to see if I can talk about it, or I will include resources in the assignment that I can look at. Okay. So these are the things we're going to talk about. Let's talk about array very quickly. Array, you know very well the definition, just a sequence of index element. Whenever you want to get to a particular index, under the hood, or behind the scene, you just have to calculate what's the relative address and go there, right? That's what you learned in 2031, you know, in the C course. And the size of an array, whenever you create the array, should be fixed. That means you can resize the array, but it's going to be some very expensive operation to do. Because every time you resize the array, you got some strictly larger array. You still want to copy over the old array into the new array. That copy operation is going to be expensive. All right? That's something I will also need to visualize a little bit later. And I want to give you guys some heads up over here. People still do array resizing quite often for the Java library collection. For example, let's say array list. They do have array implementation behind the scene. The way they talk about resizing, I believe, is something called doubling, right? So here, don't need to be troubled too much about increments or doubling. I just want to mention the two terms to you. So people usually, if they want to implement their data structure using arrays, they got two options usually, common options for resizing, either called the increments approach or doubling approach. One of them, if you try to argue about the average case, when I say average, it's more about expected value. Right? If you talk about average case, one of them turns out to be constant as opposed to linear, which is very efficient. Right? I'll see if I can give you some guidance about these two strategies. We'll see how the coverage is going to go for the lecture. Right? But for now, just heads up about these two. All right. So what will be the operation for the array? So you got accessing the array. In that way, you just calculate the address. That'll be constant operation, big O of 1. If you just want to update some position there, that one there, just do some variable assignment, that will also be just constant operation. The expensive one comes whenever you want to insert something in the middle of the array, or you want to remove something out of the array. That's going to be some expensive operation. So what I want to show you is about inserting by diving into some details. And we can do the practice again about deriving asymptotic upper bound once more. We'll do that. All right, so a code fragment that we're going to talk about will be this one here. Okay, we'll see. We'll definitely try to go as much as we can for this example here, and then we'll continue from Thursday. But we got 14 minutes. Okay, let's see how much we can do. All right, so here we got insert at. This is the method we are analyzing. That one there takes one input array and returns another array. Takes an array as input, returns an array as output. So this n here will be the size of A, right? Just our convention, just for easy analysis of the runtime. So this will be A.length. And then we got E and I over here. E and I over here simply say, I want to insert into index I the element E. Okay, I'm going to show you an example. So this one tells me that I want to insert element E to index I. And we are making the following assumption. Okay, let's say if you got an array over here, let's say this is the array. If I say I want to insert at, I pass over here 0. That means I want to insert right in the beginning. On the other hand, I can also say I want to give the value n. Let's say, for example, I got 1, 2, and 3. I say I want to insert index 3. 0, 1, 2, 3. I want to insert it as a last. Right? So both 0 and n will be the extreme values, will be the bounds for I. So this is something important when we try to figure out the runtime. So this would be 0 less than or equal to I, less than or equal to n. 0 here means we want to insert first. And this one here, we want to insert at last. All right? So these are the two boundary values for I. All right? I would suggest we try to understand the algorithm a little bit before we try to derive the running time. But again, in order for you to derive the bounds, you don't need to understand how the algorithm works. But let's do that anyway. So this is one example here. Okay, this one here. If I want to insert, let's say the input array is Alan, Mark, and Tom. Okay, let me just keep track of the time. Good. Okay, sorry. Give me one moment here. Good. If I got Alan, Mark, and also Tom over here, right? That's the input array. You can see the size of the input is simply 3. I want to insert Jim at index 0. Index 0, as you can see, is over here. So think about a 0 over here is I. All right? So that means Jim should be inserted in the new array. Oh, by the way, before that, given that input array is of size 3, I'm going to create an larger array of size 4 with one extra slot for me, right? That makes sense for the new element. And then what's going to happen is, you can see after index I, which will be 0, what should I put over here? It should be whatever element that used to be in the input array over here. So that means Alan should really go to here. Mark should go to here, and Tom should really go to here, basically. All right? So what's going to happen is I'm going to have this index 0 in the input array should be copied to index 1 in the output array. Index 1 should really go to index 2. Index 2 should really go to index 3. This is exactly what you will see in this line of code over here. All right, I'm just trying to show you why it should be done that way. It's a very basic operation, just to shift everything to the right by one position. Right, so after that, I'm going to get over here, I'm going to get Alan, Mark, and Tom. So in this simple case, we just want to add Jin into the first index, index 0, whereas all the original element will just be shifted to the right by one position. Right? That's how it works. And let me just trace one more time. I'm going to trace the algorithm line by line, and I'll do another example. Okay, all together. Okay, let's take a look. The line, this line here, we are just creating a strictly larger array. So size 3 is now become size 4. Right? I didn't really include this one in the list of primitive operation, but object creation is really a primitive operation, right? Just allocating memory. So you can think about this guy over here would just be 1, just this line. So I'm going to put 1 here, and I'm going to put it aside. Whenever we talk about object creation, by calling the constructor, we go of 1. Okay? Just creating the new objects, basically. Okay? In this case. So line number one, this one here is good. So now we got different phases. We got phase number 1, phase number 2, and phase number 3. And eventually we return the array. So for the last line here is also going to be 1. Let's write it down first. And then we're going to analyze how phase number 1, 2, and 3 are going to be figured out. All right, so 1 here as well. Let's now look at phase number 1, which I'm going to highlight in green. This part over here. Right? This one tells me I am actually going to go from 0 all the way to I minus 1. How many iterations are there? I iterations, agree? What's I? Somewhere between 0 and n. So what's the worst case for I? N. All right, you can see the connection here, right? Okay, I'm going to write it down in a moment, but let's see exactly what's going to happen. Now I want to insert, I still got the same input array, Alan, Mark, and Tom. I still got Alan, Mark, and also Tom. I want to insert Jim over here into index 1. All right, you can think about index 1 is actually over here. Right? Index 1 is actually over here. What's going to happen is I know that Jim, after inserting, Jim should really go here. This one's easy, right? That one we agree. So this one here is really this middle stage, right? This one here is really just 1. Let's write it down first. What's going to be something you got to think about will be the before stage and after stage. If I want to insert Jim into index 1, that means anything that goes before index 1, for example, this will be I minus 1. We should copy that to here, before that. Anything that goes starting from index 1 over here, they should really go to here, after index 1. That's basically what we're doing, right? Good. If you see the conceptual idea, that's great. So I'm going to do some coloring over here very quickly, and then we'll figure out running time. Think about this one here. I'm just going to put it in blue. Okay? So what's going to happen is before index 1, we got Alan. Starting from index 1, we actually got Mark and Tom over here. So for this particular loop over here, it's actually going to copy whatever that's before index 1, which will be Alan in this case. It could be multiple in general. Copy this into over here. So it's going to be Alan. And when we move on to this particular loop over here, it's going to start from I plus 1. I plus 1, this is I, so this will be I plus 1. So this is I, starting from I plus 1. I'm actually going to say Mark should be copied over to here, and Tom should be copied over to here. Right? You can see this exactly 2 versus 1, and 3 versus 2, like a one-off indices, exactly over here. That's something I'll leave to you to really study. All right? So that one there, I'm going to get Mark over here and also Tom over here, right? So you can see exactly the correspondence over here, Mark and Tom, and also Alan. Right, that's very quick tracing, right? Didn't really go into 100% detail, but that's something you should be able to following the code line by line and then try to see how that works. And let's now figure out the running time, all right? Let's now do the following. Let me start with this one here. The body of the first loop, what will be this, each execution? 1, agree? Just array indexing and maybe some variable assignment, so just 1. But how many iterations do we have? As we said earlier, it's going to be from 0 to I minus 1. So that would be exactly I iterations. We know that I, in the worst case, is going to be n. So that means in the worst case, it's going to be n iterations. Right? So this is very crucial for you to realize over here. Okay, so that's the number of iterations for the first for loop. What about the second for loop over here? It's going to be from I plus 1 to n. Right? Let's specify the closed interval. We got I plus 1, n. All right, so now this one might be the one we need to apply the formula. How many integers do we have in this closed interval? Okay, anybody tell me? Not exactly. N minus I plus 1 plus 1. Okay? And so here we got n minus I, and we got minus 1 plus 1 cancel out, so only n minus I. All right, guys, it's okay to be struggling a little bit now, but you really got to make sure you kind of get it. Okay, so that's going to be n minus I iterations. And I'm going to actually write it down. All right, so now we got all the information we will need. And then we're going to figure out the running time. Okay, I'm going to put it right here. It's going to be big O of, so going to be 1. So this will be, so this 1 here is the 1 here. Plus, the number of iteration for the first for loop will be n. The body here will just be 1. N times 1. Plus, here we got this 1 here, right? Plus, the second for loop, the number of iterations n minus I. So we got n minus I, and then times 1 over here. And then finally, we got 1. Right, like that. And then, if you try to see that, what's the highest power? Well, you can see power of 1. This is also power of 1. Because n minus I times 1, just n minus I, would still be, something close to n. So overall, it's going to be n. Okay, you can drop all the lower terms, etc. So the final answer you will get will be big O of n. This one tells you, in order to really insert something into the array and do all the necessary copying, shifting, etc., it's going to be a linear operation. Okay, very important for you to really understand. Okay, and then you guys can try maybe insert at over here. So this one is the worst case for. So let me just give you some insight over here you can think about. This one here is really the worst case for the second for loop. And this one over here is really the worst case for the first for loop. Okay, I tell you just this one here. The reason that this will be the worst case for the first for loop, simply because you're going to do the number of copies that correspond to 3, which is the size of the input. Okay, and then as to why this will be the worst case for second for loop, I'll leave you to think about. And the sorting problem here, just going to conform to the computational problem format. We got input and we got output. So here we say input is going to be an array of n numbers. And we want to return the output, basically the same array, but it has been sorted according to the so-called non-descending order. All right, you may have seen this term before, but now, even before we talk about sorting algorithm specifically, I want to clarify this term very quickly and do some exercise together with you. Sorting problem may require different sorting order. All right, so you got to watch out. So there are at least these 4 possibilities. Non-descending, which is what we're having. Ascending or increasing. Also non-ascending, and also descending or decreasing. Right? So these are the 4 possibilities you might see for your sorting algorithm. Of course, given a particular one, you have to adapt your algorithm accordingly. Usually, it will not be very difficult to go from one order to another, but you got to know exactly what it means mathematically. That's something I want to do first, and then do some exercise with you. All right, let's now take a look at these 4 orders, right? They are very straightforward, but you just got to know the definition very thoroughly. All right, so I got these 4 possible sorting order. I got decreasing, descending. I got increasing, ascending. Let's talk about these 2. These 2 are very straightforward. Decreasing, descending simply means the values of the array should have this downward trend. All right, let me write it down here. That means it should be this downward trend, always downward, strictly decreasing. And if you say this is element at index I, its immediate to, the element to its immediate right. Let's say A, I plus 1. So in this case, we should have the larger than relationship, right? AI should be exactly strictly larger than AI plus 1. One example. 5, 4, 3, 2, 1. And if you look at, for example, 4 and 3 over here, you can see that's exactly the larger than. Easy. Symmetrically, when we talk about increasing ascending, it will be just the other way. It's going to be the upward trend rather than downward trend. So that one there, let me also write it. Okay, upward trend. So this will be, for example, AI to its immediate right, AI plus 1. Right? Obviously, that's going to be smaller than. Notice that there's no equal sign. Right? One example will be 1, 2, 3, 4, 5. And you can see that, for example, 2 and 3 over here is exactly that smaller than. The smaller than relation should really hold for every consecutive elements. The tricky ones will be these two. The way to think about it is being a little bit more logical to derive what's really happening here, just in case you forget. Let me just use the non-descending as the example over here. Okay, so this one here, non-descending. Okay, the way I see it is like this. When I say non-descending, the non here really corresponds to the logical operator for negation. Not the case descending. All right? So the way to work out the logic is, okay, by definition, it will be not the case descending. And we just learned that for descending, which will be this case, it should be AI strictly larger than AI plus 1, right? Let's apply that. Equivalent to, not the case, AI larger than AI plus 1. Now we can distribute the negation over larger than. I'm pretty sure you know. That should be less than or equal to. Equivalent to AI less than or equal to AI plus 1. So this is the formal definition for non-descending. And you can work out the logic for non-ascending in a similar fashion. I'll leave that to you. Very straightforward to derive that. Based on this, let's now visualize it quickly. Okay? So now we got non-descending over here. How do we visualize it? This is to say, it just cannot go descending. As long as you're not really trending downwards, you'll be okay. What does it really mean not to trend downwards? You can either trend upwards or no trend, flat. These are the two possibilities. All right? So I'm going to write it down here. So it could be, for example, trending upwards, or it can be flat, or it can be trending upwards again, right? Like that. So if you think about maybe this is A at index I, this is A at index I plus 1, and this may be A at index I plus 2. Right? You can see this one here is less than, and this one here is equal to, right? Exactly corresponding to less than equal to over here. All right? One example. 1, 2, 2, 3, 4. 1, 2, 2, 3, 4. Right? Obviously, you can see the 2, 2 over here is the equal, the flat. And also maybe the 3, 4 over here is the example where we're trending upwards, less than. All right? The last one will be just symmetric. Okay, let me just write it down for completeness. That one there is simply just going to be larger than or equal to. All right? So as long as we are now trending upwards, we'll be okay. So we can either be trending downwards, stay flat, or trending downwards again. Okay? So now if you try, let's say A at index I, so this will be A at index I plus 1, and also here A at index I plus 2. Let's see. So this one here is less than. This one here is just equal to. Okay. Oh, sorry. I really meant to put this guy here to exactly here. Okay. Sorry, it's a bit mess. AI plus 1, less than. AI plus 1, AI plus 2, equal. All right. Hey, let's see one example quickly. And the one will be 4, 3, 2, 2, 1. 4, 3, 2, 2, 1. So you can see again, this will be the equal here. And this will be the trending downwards. Like that. All right, any question about the definition? Yeah.
So what if you wanted to sort in a decreasing or increasing way a list or an array that has duplicates? Would you get rid
That's a
of
good question. That's a very good question. So now there's some very important insight which I'm about to say. Apparently, you can see for decreasing or increasing case, the array should not contain any duplicates, in which case it got flat. It should not be allowed. So that will be so-called a precondition for the input. If the input itself already contains duplicate, it should not be valid even. You don't really want to remove the duplicate for the input. Yeah. Oh, we'll talk more about it later. Just bear with me one moment. So here, so the for decreasing and also for increasing, so these two, there'll be no duplicate allowed. On the other hand, for the non-descending and also non-ascending, these two, duplicates will be allowed. Duplicates allowed. Specifically, duplicates for consecutive elements, because you stay flat, right? Question somewhere? Yes?
By like convention, when like demonstrating algorithms for the first time, would you do it in a decreasing or increasing?
You know, I would say for sorting, you know, it really depends on what you need. You know, let's say for student record, right? Sometimes you may want to see from the maybe highest performance to the lowest performance. Sometimes you may want to see the other way. It really depends on application. Nothing wrong with either one of them.
So learning it for the first time, would you want to do ascending or descending? Would not matter.
Doesn't really matter. But you know, just say for the selection sort, insertion sort we're going to talk about today, we're going to do non-descending. Yeah, non-descending. Yeah, just get used to the term. That's my point, right? Yeah, guys. So in the test or exam, either of these four is possible, right? You got to be very clear about which one is which, right? That's why I really want to spend time making sure you're fine with this. All right. Any question about the basic definition? Question for you. There we go. Oh, again, you know, this is really unfair to you guys. I forgot to include that again from my notes. Okay, that's really unacceptable from my side. Okay, just give me one moment. So there is really a problem which I want to solve together with you. Just give me one moment. I'm going to get it within 10 seconds. Okay, this is one here. Somehow it's lost. Okay, bear with me. So let me just retrieve here. There we go. There we go. I'll make sure I double check the notes before I present for a second section. It should not happen. Yeah, I'm just copying that. Bear with me. Basically, the exercise I want you guys to try is to think about two sets of array, and then to decide how can we formulate a relation between the two, right? As soon as the copy is done, and then I'm going to show it to you. Sorry, take some time. Okay. Almost there. Okay. All right. Good. There we go. There we go. And then I'm just going to just clear that. And then this will be completely clean. Okay, again, my apology. There we go, exercise. All right, so here we got two sets over here. And set number one, S1. That one contains all the possible arrays sorted in the non-descending order. Set number two. all the possible arrays sorted in ascending order. All right, try to recall the definition, right? Exactly, right? So now we got set 1 and set 2. Conceptually, they're infinite because there are infinite number of arrays that may be sorted in a particular fashion, right? Now we want to formulate the relation between these two sets. What would be the symbol to use? Or if you simply think there's no relation between them, maybe the intersection is simply empty. That's another way to say it. This is a very nice one to test your understanding about the definition. Of course, if you're still getting used to it, that's fine, but I just want to see if anybody would like to suggest anything. Okay, I'll pick one here. Go ahead.
Would S2 be a subset of S1?
Are you suggesting something like S2 subset?
Sorry, would it be proper subset?
You tell me.
Yeah, it'd be proper subset because not all non-descending.
Okay, not bad, not bad. Maybe that's what you're thinking as well? Okay, good. So guys, pretty good. Your fellow student was right, but let me elaborate on why this should be the answer, right? It's okay if you're still getting used to it, but think about different combination, right? I might ask you different combination. Right? So this one here is actually correct, but we're gonna see exactly how this is the case. Whenever you want to show proper subset, okay, this is what you gotta show. So let me just make a little bit color here. So let's say S2 is over here. And also S1 is over here. All right. So let's say S2 is a strictly smaller set. And S1 is a strictly bigger set over here, right here. Okay. And then we're saying that S2 are all the arrays sorted in the ascending order. So this will be about ascending. Versus S1 over here would be in the non-ascending order. S1 in the non-ascending order. If we claim that the relationship should be proper subset.
Isn't it non-descending?
Non-descending, yes. Oh, I said non-ascending, right? Thank you so much. I definitely didn't mean that. Thank you. Thank you so much. Yeah, for sure. Right, so now if we say that it should be a proper subset, what does that mean? That means there should be at least one member over here we can show that belongs to S1 but does not belong to S2. All right? So that's the member we ought to show. There is an array in that's actually in S1, but it is not in S2. All right? Give me one example. What would be such array like? All ones? Okay, I like that. Basically, it's not really, it's not just strictly increasing, basically. For example, 1, 1, 1, and 1. Thinking this way, when we talk about ascending, right, it should be the less than relation. When we talk about non-descending, it's really the less than or equal to relation. So what really stands out in S1 is about the equal sign here. So if you got any consecutive element that actually shows you the flat curve, that would not belong to ascending. All right? Question about this? Okay, I hope that's straightforward. That's important, right? So just get ready for different combination of the orders, right? You really want to see what's the relationship between different orders. Which one, for example, this one should be more specific and this one is more general, right? About non-descending. And we're gonna do non-descending sorting today.